Hi guys, Buildzoid here, and today we're going to be taking a look at some of the differences and mainly the improvements of DDR5 compared to DDR4. So we're going to be taking a look at the new bank group configuration, and the 32-bit memory subchannels, and the new refresh option, and also the on-die ECC. Um, so yeah, let's get into it. We're going to start with the bank groups, and the reason we're going to start with that is because to me that's the most noticeable difference with DDR5 compared to DDR4. So on DDR5, actually let's start with DDR4, and for some reason this is on the wrong page. Actually, I know why it's on the wrong page. I've tried to do this video several times and it keeps falling over. Um, Anyway, DDR4 has 4 bank groups per DIMM. Unfortunately, unlike the DDR5 documentation, it's not explicitly mentioned here, but it is internally configured as as also that this should be an A instead of an AN, but you know, I'm not a well, whatever. As a 16 bank DRAM with 4 banks per bank group. So if you have 16 banks in total and each of them contains 4 banks, each bank group contains 4 banks, you've got 4 bank groups in total. And this is true for X4 memory chips and X8 memory chips, and it's not true for X16 memory chips. X16 memory chips only have 2 bank groups, and because of that, X16 memory chips suck for performance. I have a video going into more detail on that. So yeah, basically with DDR4, you could have either 4 bank groups or you could have 2 bank groups, and if you care about performance, you want 4 bank groups. Now, with DDR5, we get sort of 2 different configurations depending on if you have like low density DDR5 or high density DDR5. Now, I'm not aware of any 8 gigabit DDR5 memory chips. As far as I know, nobody produces those because DDR5 is expensive and low density memory chips are not very profitable. Right, like one of the primary customers for DDR5 is like servers, and servers want more memory, not less memory. So, yeah, right now all of the DDR5 that's being produced is 16 gigabit memory chips, not 8 gigabit memory chips. That becomes kind of, we'll get to why that's sort of significant. But anyway, for 8 gigabit memory chips, if they ever make any, you can either have 16 banks organized into 8 bank groups with 2 banks in each group, and this is for the X4 and X8 devices. And this does slightly affect the new refresh functionality that DDR5 has. But ultimately, we don't really care about this. The important part is that there's 8 bank groups, and then there's also the X16 chips, and those suck as usual. Except they suck less than they did on DDR4, because with DDR5, those the bank group count gets cut in half again. So you go from 8 bank groups to 4, but that's less of a downgrade than going from 4 bank groups to 2. It is still a downgrade, but it's not quite as bad. So yeah, you've got 4 bank groups on the X16s, and then for the higher density memory chips like 16 gigabit, 24 gigabit, and then I think the specification allows all the way up to like 64 gigabit DDR5 chips, maybe even larger than that, but I don't know. Like for now, I've seen 64 gigabit. I can't remember seeing 128 gigabit densities. Anyway, so for like normal size DDR5, because currently, as I mentioned, these don't really exist, or like they literally don't exist. I've not seen any. I don't know where you would buy one. So for normal size DDR5 memory chips, you get 32 banks organized either as 8 bank groups of 4, or if you get a 16X chip, you get 16 banks with 4 bank groups of 4. So, yeah, we get more bank groups with DDR5. We get literally twice as many bank groups as what you got on DDR4. Now, the X16 memory chips, you can get those, and you get those on 8 gig DIMMs. So this is a example of a memory stick that would use X16 memory chips. And what you'll notice about this is it's an 8 gig DIMM, and you should avoid it. And the easiest way to tell if you have a X16 DDR5 memory stick is that it has 4 memory chips on it instead of 8. A proper memory stick has 8 memory chips on it. If your memory stick has 4 memory chips on it, it's bad. Really bad. Like, basically, like, if you're considering buying an 8 gig DDR5 DIMM, you should actually just buy DDR4 instead. Um, yeah, just get DDR4 instead, because the whole reason we have these extra bank groups is because it boosts performance. Um, and the reason it boosts performance is because of the timing parameters, and some idiot. Well, luckily this timing's pretty easy to find. There we go. So, yeah, basically your memory controller, or more like your memory, has a bunch of, well, memory and memory controller. Ultimately, the memory controller kind of has to respect the timing delays, otherwise things don't work. Anyway, so you have timings like, for example, read-to-read delays. And so you'll notice that, and this is the Intel documentation for the 12th gen CPUs. So on your 12th gen CPU, you have a timing, for read-to-read operations on a different DIMM. So this is for if you're using multiple memory sticks on the same memory channel. Yeah, we're going to go with same memory channel. There's 32-bit subchannels with DDR5, but they're not real, like... Imagine if they had, like, better terminology for this stuff. Anyway, then we have read-to-read different rank. So this is just for accessing a different rank of memory, or, like, reading from a different rank of memory on the same memory stick. And then reading from a different group, and then same group. And this is why having more bank groups is significant, because the different group timing and the same group timing are actually very different. On default settings, the different group timing is typically going to be 8 clock cycles, whereas the same group timing is going to be 16 clock cycles, which basically means if you do a back-to-back read operation, so you read, basically what you're going to be sending to the memory is, hey, I want to read from X, and then you're going to send, hey, I want to read from Y. Well, if Y is in the same bank group as X, you're going to basically end up waiting 16 cycles between those two read operations. Whereas if Y is in a different bank group from X, you can actually do that in 8 cycles. So you can do, read X, wait 8 cycles, read Y. And then after some delay that we're not going to get into right now, you're going to get your data from both X and Y, plus that, 8 cycle gap between them. Now, if you're doing a read-to-read on the same group, well, you're going to say, hey, I want to read X, and then you're going to wait 16 cycles, and then you're going to get to read Y. So, pretty significant delay, significantly reduces your memory bandwidth, and this is why you want to have a lot of bank groups, because the more bank groups you have, the greater the probability that the next thing you want to access is not in the same bank group, and therefore you're going to be using the different group timing, which also gets referred to as the short delay, as the short timing. So if we go to page 120, we have the activate command, which is a different timing, but it has the same principle behind it. You have like TRRDS short is used for timings between banks located in different bank groups, and then you have TRRDL long, and that's used for timing between banks located in the same bank group. So this is the whole reason why having more bank groups is good for performance. You can basically chain certain commands back to back a lot more quickly the more bank groups you have. And this is also why on DDR4 there's quite a performance uplift by having a dual rank memory configuration, because each rank of memory, assuming that you're using X8 memory chips or X4 memory chips, is going to have 4 bank groups in it. And so if you go from single rank to dual rank, in total you end up with 8 bank groups. And on DDR4, that means you get much more memory performance. With DDR5, however, because we already start with 8 bank groups, you actually don't really see much of a performance benefit by going from single rank to dual rank. And the reason for this is with 8 bank groups from the get-go, as well as some of the other optimizations that DDR5 has to improve sort of data efficiency, or data bus efficiency, I guess you could call it. Going from single rank to dual rank on DDR5 really doesn't achieve much of anything. So with DDR4, the reason why going from single rank to dual rank massively boosts performance, and I have a video, actually I have multiple videos showing this. Hopefully I'll remember to link some of them somewhere, hopefully below the video. But basically, with a single rank of DDR4, the data bus is not actually anywhere near saturated. Well, it's pretty heavily utilized, but it's not anywhere close to being maxed out. Whereas with DDR5, because you have 8 bank groups from the get-go, you're very close to maxing out the data bus as is with just a single rank of memory. And so on DDR4, you go from single rank to dual rank, you get this huge performance uplift, whereas on DDR5, you go from single rank to dual rank, and it just doesn't do a whole lot of anything. It's actually very similar to what happens when you go from like dual rank DDR4 to quad rank DDR4, which basically is the same difference. You go from having 8 bank groups across 2 memory ranks to having 16 bank groups across 4 memory ranks. But going from 8 bank groups to 16, it's like you are already basically maxing out the available data transfers on the data bus with the dual rank configuration. So going from dual rank to quad rank doesn't really give you any more performance per clock because there isn't a bunch of wasted clock cycles any longer. Whereas in a single rank configuration, you have a lot of wasted clock cycles. And then obviously, if you get like your X16 memory chips, those are horrible. You have 2 bank groups, so you're wasting even more clock cycles. That's why these are so freaking slow. But yeah, if you have X8 in dual rank on DDR4, it's like that's sort of the ideal for performance as far as I'm concerned, and also from an overclocking perspective, because one of the biggest penalties to quad rank is like it doesn't really improve your performance per clock, and it drastically reduces the maximum memory speeds that you can run. Because it just puts so much more load onto the memory controller, because with DDR, the way the extra memory chips get connected to the memory controller is they just get connected in parallel. So if we scroll down through, hopefully, I think it's this, yeah. So if we scroll down through this data sheet, right? So DQ, this is the data queue. And basically you can see that the DQ of like U14 is actually connected to the DQ of U7, right? And then DQ goes all the way out to your actual CPU's memory controller. And so when you have a dual rank memory configuration, you literally have two sets of memory chips connected to the same data line at the same time. And then if you go up to quad rank, well, now you have 4 memory chips attached to the same data line, and all of the parasitics that are associated with that. So the capacitance of the inputs, the wire that connects the memory chips to the the extra like wire that connects the memory chips to the memory controller. And like, to be fair, like the memory chips in multi-rank configurations, like you do have the memory chips have termination resistors to like minimize reflections and that kind of thing, but that still doesn't change the fact that you are just putting more and more load on the memory controller the more memory chips you connect to it. So with DDR4, going from dual rank to quad rank is basically a performance downgrade. With DDR5, that happens basically going from single rank to dual rank, because going from single rank to dual rank, you don't really improve your data, like your data bus utilization doesn't really change that much, but your overclocking headroom tanks. Because DDR5 runs at much higher speeds to begin with, and so it's already, like, DDR5 is just much more sensitive in general in order to be able to run at high speeds compared to DDR4, because it just runs at very high speeds, and so consequently it's a bit touchy when it comes to stability requirements. And so this is, in my opinion, sort of the main difference between DDR5 and DDR4, where it's like single rank DDR5 is very fast. Like clock for clock, it performs really, really well compared to dual rank DDR5. And as far as I'm concerned with DDR5, there's really no reason to go from single rank to dual rank unless you need the extra memory capacity. With DDR4, of course, it's very different. You do actually want dual rank, but with DDR5, single rank might actually be just optimal for a while. So that's really, really cool, because one of the big benefits to this is that single rank DIMMs are always going to be cheaper, and actually the performance uplift is literally one of the main reasons why DDR5 has this new bank group configuration. Like, DDR5 is literally meant to be an upgrade to DDR4, so, like, design efforts went into just making it better. By using the available data transfers a lot better, by having more bank groups across which to sort of chain memory access operations. So, yeah, so that's sort of the first difference that I think is noteworthy between DDR5 and DDR4. Then we get the subchannels. So if we go to the UDIM core documentation from Micron here, with DDR5, like non-ECC UDIMs, so unregistered DIMMs, you have two 32-bit subchannels. Basically, each memory stick has two. So with DDR4, your memory stick is 64 bits wide. With DDR5, your memory stick is still technically 64 bits wide, but now it has two separate like control groups, which is 32 bits wide each. And so the big benefit, well, so there's electrical benefits to this, and there are also, again, sort of data bus efficiency benefits to this. So the electrical benefits of this is that on DDR4 DIMMs, the command address bus, which enters the memory stick through sort of the middle, like this middle area right here, the command address bus would basically have to connect to all 8 of the memory chips, and typically the way it would do this is it would go up the memory stick, then come over to one side, and then circle back all the way to the other end. So you had this very long command address bus, and it's not really ideal for signal integrity. And so with DDR5, by having these 32-bit subchannels, where each memory channel is actually only, connecting 4 memory chips instead of all 8 of them, you now have a command address bus that you have 2 separate command address buses, right? Because each channel has its own command address bus. So the command address bus comes up on, like they both come up through the middle of the memory stick, but now one of them shoots off to like this side of the memory stick, and the other one shoots off to the other side of the memory stick. And that is one of the sort of big electrical improvements with DDR5 that allow it to run so much higher memory speeds than DDR4. So that's sort of the electrical benefit of the 32-bit subchannels. But there's also an efficiency benefit to the 32-bit subchannels, and this is because DRAM operates on bursts. So you can't actually read like a single byte of memory from a memory stick. You can't do that. It's not possible. When you send a read command down the command address bus, you get sent. So with DDR5, the standard length is burst length 16. Technically, there's also a burst chop, but we're not going to get into that because it's like complicated. So the standard read command length is a burst length of 16. So you send a read command and you send some address information, and then the memory stick is going to spit out 16 bits of data per pin. So on DDR5, what this meant, because DDR5 actually used different length reads or had different burst lengths. So DDR4 used a burst length of 8. And a DDR4 memory stick was 64 bits wide. If you were sent a read command to a DDR4 memory stick, you would get back 512 bits of data. Now, if DDR5 still used 64-bit wide memory sticks with its burst length of 16, instead of what we have with the two 32-bit independent memory channels, you would be getting sent 1,024 bits every time you send a read command. And reading 512 bits every time you want to read anything, it's not exactly the most efficient thing in the world, but it does mean that you have good memory bandwidth if you're reading large amounts of data that happen to be sequential inside the memory, right? So if you're reading like an image from the memory into the CPU or something like that, the long burst length is actually beneficial in that scenario. It provides extra bandwidth. But there's a sort of compromise that needs to be struck between having good memory bandwidth and reading way more stuff than what you actually wanted on smaller read operations. And so with DDR5, with the longer burst length, in order to maintain that sort of 512 bits of data per read, we now have the 32-bit memory subchannels. So now, if you want to read just a single byte of data, you still get 512 bits of data, but that's more efficient than reading 1,024 bits of data every time you want a single byte of data, right? A byte being 8 bits. So, yeah, and evidently, 512 bits per read seems to be some kind of, happy sweet spot that the CPU and DRAM manufacturers agree on. So this is how DDR5 memory sticks function, is just you have the two independent channels, so you can send like well, the other benefit is you can send completely independent commands to each of the memory channels, right? So you can be reading on one memory channel while writing on the other memory channel, or you can be reading from address X on one memory channel while reading from address B on the other memory channel. So basically, it allows you to it allows you to sort of access the memory a lot more efficiently. Um, so yeah, on a given memory stick. And then of course the CPU, like technically the DDR5 memory controller on like a 12th gen CPU is quad channel. However, and also technically some motherboards would allow you to disable some of some of the 32-bit subchannels. So you can technically configure a DDR5 motherboard to run in single channel mode or triple channel mode. You should never do this because especially like single channel is justifiable if you're going for like a memory speed record or something. Triple channel is not justifiable. There is no reason to ever run a DDR5 system in triple channel. That's terrible. Don't do that. So yeah, so the 32-bit subchannels basically are a means of sort of keeping the excessive data reads and data writes, because the thing is, like, you're always going to be, everything is done in bursts. Nothing, you're never going to be sending like 1 bit of data to the memory at a time. Everything is done in bursts. So the 32-bit subchannels are sort of like, they're an electrical design improvement, but they're also a sort of efficiency improvement in that you don't have to read or write way more data than you actually wanted. So that's another reason. And then, of course, you can just do multiple operations at the same time. There is a funny penalty to having a bunch of independent memory channels, and that is that your worst case scenario memory latency actually gets worse. Or more like your memory latency for single accesses gets worse, because if basically the CPU has to go and like find which memory channel your stuff is on. Not really, but basically, like, the thing is, for the longest time, the way the mainstream Intel memory controller worked was it was actually 128 bits wide, single channel. It didn't really behave like a proper dual channel memory controller, and one of the benefits of this was that it had really good latency at the cost of just kind of like, you had a lot of random data access that you wanted to do. It was kind of terrible at that, which is probably one of the reasons why it's benefits so much from going from like single rank to dual rank, because if you have dual rank and you have all of these extremely inefficient operations because the memory isn't real, like, you can't do independent memory access properly, you can at least chain your incredibly inefficient operations, back to back more to make them slightly less, well, they're not less wasteful, but you have more opportunities to actually get the stuff you're looking for. But one of the reasons why Intel had this sort of like not really dual channel configuration for so long is it actually has latency benefits. It has slightly lower latency if you're only trying to access 1 byte of data. I am not entirely certain why. And funnily enough, there are certain DDR3 platforms where you could actually toggle between true dual channel functionality and like overgrown single channel. It's not an option on DDR4. As far as I know, Ryzen has always been like true dual channel. The HEDT platforms from Intel were always true quad channel, and Intel mainstream until Alder Lake was giant single channel, as far as I know. But basically, Alder Lake running DDR4 is true dual channel, like two completely independent memory channels. And then on DDR5, it's 4 completely independent memory channels. And unfortunately, that does mean that like a single memory access latency is slightly worse. The trade-off is you can now interleave a bunch more memory operations, and so for certain workloads, it offers a just huge performance uplift. So yeah, this is just like across the board, just DDR5 is supposed to just straight up be faster than DDR4. It's just that the one issue DDR5 has right now is going from DDR4 to DDR5. well, you can see it in the read operation right here, right? Like, if I want to do a read, I send my read command and I send my address, and then I wait for the cache latency before the data actually shows up, right? So if you're doing a single read operation, it takes forever because your cache latency for DDR5 as standard is like 40 clock cycles, right? Whereas with DDR4, your cache latency would be like 22 clock cycles for 3200 megabits per second JEDEC spec. And of course, high-end DDR4, you're looking at like, 3800 megabits per second with 14 clock cycle cache latency. And then it's just like, well, yeah, that's going to be a lot quicker than sending a read command, waiting 40 clock cycles, getting your data back. But then where DDR5 sort of, picks up is that since you have all those bank groups, if we scroll down to, it's a few pages from here. Nope. A few more. So yeah, if you do a read to read with a different bank group, you can do a read command, right? And so from this command, it's going to be another 40 cycles before you actually get your data. But while you're waiting those 40 cycles, you can actually just send another read command within, depending on what your CCDS timing is, which Intel doesn't have a CCDS timing for this operation. That would be we'd be looking at the TRRD DG timing for that. So basically you would wait 8 clock cycles here, and then you send another read. And I'm not sure how many you can chain in a row, but you can basically do that. Yeah, and then if you're doing it for the same bank group, well, then you do your read, and then you'd have 16 clock cycles of delay, and then another read. Yeah, so that's how DDR5 do. And actually, this is also the same with DDR4. So, yeah, that's why right now DDR5 really struggles against DDR4. It's just like that delay between sending a read command and then data actually showing up is kind of painful. So anyway, the next thing I wanted to talk about is the new refresh functionality. So if we go to page 169, we have the refresh operation. And the way the refresh operation works is basically memory sticks are volatile. And the reason they're volatile is because they use tiny little capacitors to store your ones and zeros. And this is not a problem when storing zeros because zero is literally like a low voltage. So, the capacitor naturally is going to sit at a low voltage. Ones are a bit of a problem because the tiny little capacitors making up your memory stick, they leak charge over time. So if you charge them up to write a 1 and you let them sit there, eventually they will revert back to being a 0. And so DRAM has the refresh operation where periodically the memory will, read all the, well, it won't actually read all the data, but it'll basically rewrite all of the data that's in it so that it doesn't disappear. And the way this works on DDR5, like on DDR4, is you basically have a refresh cycle timing, which is called TRFC, and you have a refresh interval timing. And basically what these describe is, hey, every TREFI clock cycles spend TRFC clock cycles refreshing the data. Now, the thing with this is on DDR4, this would actually hit I think it would hit all of the memory sticks at the same time. So when the memory was refreshing, it was refreshing. You could do nothing. You couldn't read, you couldn't write. Basically, if there was any kind of memory accesses that you wanted to do, you weren't doing them because the memory was busy doing its little refresh cycle. And typically refresh cycles for DDR4 are anywhere between like 200 clock cycles and several, like 800, even. I don't think I've ever seen an actual necessity to run 1,000, but at very high DDR4 speeds, you're going to be looking at like 600 to 800 clock cycles of refresh cycle time. And then, after your refresh cycle time, you would have your refresh interval again. And your refresh interval is thousands of clock cycles. Typically, like by JEDEC, it's usually somewhere between like 10,000 and 20,000. If you're manually setting your timings, you'll typically see people using from like 32,000, which is the limit for Intel HEDT platforms, all the way up to say, well, actually, Alder Lake will let you set the the refresh interval all the way to 262,000 clock cycles. So you can wait a very long time before refreshing the data on Alder Lake. Now, that doesn't mean that your data will still be there by the time you refresh it, but if you have a memory, if your memory stick is capable of maintaining the data for that long, Alder Lake will let you do that. Anyway, so that's how a normal refresh works, is just like periodically all of the data gets refreshed, and while it's getting refreshed, you can't do anything. And then during the refresh interval, you can read, write, you can, do your usual memory operations, and then after the refresh interval passes, you need to refresh the memory again, or your data starts going bye-bye. Well, with DDR5, because, locking up all of the memory, like all of the memory chips so that they can refresh at the same time was deemed not very efficient, DDR5 introduced refresh same bank, which is on page 173. And that's not there. There we go. Same bank refresh. So same bank refresh, which Intel refers to as C per bank. Yeah, which Intel refers to as per bank refresh cycle, basically allows you to refresh the same bank in every single bank group. And the neat thing about doing this is that while you're refreshing a specific bank in a bank group, you can actually read and write from the other banks that aren't being refreshed, which means if the memory controller is doing a good job of shuffling, scattering the data throughout the memory banks, you actually could potentially just not have to wait for a refresh ever. Because you would never end up in a situation where the memory is just refreshing and you can't really read or write because the memory is refreshing. Well, now you are refreshing individual banks. And it's not really individual banks because it's refreshing the same bank on all of the different memory chips, right? So basically when you do a same bank refresh, if we look at our memory stick here, basically you'd be refreshing, and this is going to be specific, I believe it's specific to the memory channel. I'd have to check that. It doesn't really matter that much. But basically you'd be refreshing the same bank on U3 and U4 and U5 and U6, and that's why it's called same bank. And also you'd be refreshing the same bank in each of the bank groups, I think. Man, I did check this. Actually, we could just read it. To each banking no. Which applies the refresh process to all banks in every bank group. Yes, across all memory chips, if I'm not mistaken. And so the neat thing is you can just kind of keep reading and writing while that's going on. So yeah, again, you get to use more of your clock cycles to actually read and write data instead of wasting them all on a long refresh or a short refresh. It doesn't really matter. You don't have to sit there and wait for a refresh to complete, thanks to the same bank refresh option. Though I'm not entirely certain how often this function is used by the 12th gen memory controller. Because it does have timings for both per bank refresh, and it also has just regular refresh. And that's going to be a pain to find, yeah. Which it has a regular TRFC, which also gets used on DDR5. So, yeah, I'm not sure which one, how frequently each of these gets used, but DDR5 does have this ability that you can basically just keep reading and writing while refreshing other banks in the memory. So that's kind of neat. And then finally, we have the on-die ECC. And the on-die ECC is on page 132. And I think this explanation right here absolutely sucks. So instead, I grabbed this explanation over from Synopsys, which basically, so the on-die ECC for DDR5, the way this works, actually, you know what, this is useless. We could have just stayed on this. So the thing is, this explanation isn't particularly easy to follow. But basically what happens is, let's say you want to write a 5 to the memory. So you give the memory an address and you give the memory some data. So you say, hey, I want to write address A 5. I want to write 5 to the address A. And then you go, and so the memory gets the 5. It calculates error correction data. It stores both the 5 and the error correction code. And then the next time you want to read the 5, you go, hey, next time you want to read the 5, you go, hey, memory, I want to read address A. The memory pulls the 5 out, grabs the 5, it grabs the error correction code, it checks the error correction code against the 5 and goes like, yes, this is a 5, this checks out, it's supposed to be a 5. And then it sends the 5 straight, and it gives the 5 back to you. Now, what could happen, and the reason why we have this on-die ECC, is I send a 5 to the memory controller, and the memory controller writes down a 5, and then, the memory controller sends a 5 to the memory. The memory writes, stores the 5, as well as the error correction code. And then you go, hey, I want to read address A again, and the memory goes to address A. It grabs the data at address A, and it goes, this is a 4. And then it checks the error correction code and goes like, well, this is not supposed to be a 4, this is supposed to be a 5. And then it sends you a 5. It doesn't overwrite the 4, as far as I'm aware, but it just sends you a 5. So you get what you expected, and I believe that then, it gets corrected somehow. But anyway, so that's sort of what this is for. What this isn't for is I say, hey, you send a 5 to address A, but instead of a 5 showing up, a 4 shows up. So you have like a data bus error, right? Like somewhere between the memory controller and the memory, the 5 becomes a 4, and the memory gets the 4. It calculates the error correction code for that 4. It stores the 4, and the next time you go, hey, I want to read address A, the memory pulls up the 4, goes, yep, this is a 4, compares it against the error correction code, goes, yep, this is a 4, sends the 4 back. And the memory controller grabs the 4, sends it off to the core. The CPU core gets the 4 and goes, I was expecting a 5, and blue screens your system. So on-die error correction literally only fixes on-die errors. So anything that happens between the memory controller and the memory, or really anything that happens before the memory, just doesn't get, this doesn't fix any of that. This only fixes errors that occur in the memory. So it'll prevent things like, let's say there's like a weak capacitor, and also it'll only fix 1-bit errors. So let's say there's like one capacitor in the memory array that's kind of weak, and so you write a 1 to it, but by the time by the time it gets refreshed, it's actually a 0 now, and so it just gets refreshed as another 0. And so, then it's like, wait a minute, the data's wrong. So for that kind of scenario, the on-die ECC will actually fix it. But if you have if you have data bus errors, yeah, it won't fix that. It'll also potentially fix any kind of single bit errors that occur, like fetching the data from the memory array and getting it out the memory chip up to a point. And so yeah, so that's the on-die ECC, and basically, it does ensure that your data doesn't go, it'll correct some errors, right? It's not full error correction. If you want full error correction, you need to get 36-bit subchannels. What? How are they doing 36 bits? You'd have to use an X4 chip. I thought it was supposed to be 40. Well, whatever. Yeah, basically for full ECC, you need an extra memory chip, and so that's not on-die error correction. The on-die error correction is literally just to deal with the fact that if the DRAM manufacturer basically makes a memory chip that's a bit wonky and it just kind of doesn't always, retain all of the information, well, with the on-die ECC, it's still shippable as a functioning memory chip because it'll always give you the data that you wrote to it, even if it's not because it's actually good at storing it. So, yeah. That's the on-die ECC on DDR5, and that's basically all of the differences between DDR5 and DDR4. Is just to me, the important ones are mainly the bank groups, because it means single rank is now way more effective than it used to be. It's not better than dual rank. It's just like it used to be really inefficient. Like single rank used to be really, really inefficient, and now it's basically as good as dual rank. So that's cool. And of course, we have the 32-bit subchannels, which just means, overall the memory system is a bit more efficient. We have the new refresh option, so again, you don't have to waste you don't have wasted clock cycles where the memory's refreshing. And we have the on-die ECC, which means if you push your refresh cycle timings too low, you won't notice for a pretty long time. Yeah. I've not really, the thing is, there's no indication that you're getting these error corrections. So, and the funny thing is DDR5 does, and if you push DDR5 too far, it does have, erratic performance issues, but as far as I can tell, that shouldn't be related to the built-in error correction. So, yeah. So, anyway, that's that's DDR5 versus DDR4. Hopefully this makes sense. Yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you check them out. And that's it for the video, so thank you for watching, and goodbye.